अब एज अ होस्ट म वेद निधि दाहाल हात्तीसारियन साइन्टिफिक एन्ड टेक्नोलोजी कम्युनिटी अफ युएसए को अहिले तत्कालको यो प्रोग्रामको चाहिँ म होस्ट बन्दैछु। थुप्रै मेम्बरहरू हामीसँग हुनुहुन्छ र जति हुनुहुन्छ र अब आउँदै हुनुहुने यो कार्यक्रमभित्र आउँदै हुनुहुने सम्पूर्ण मित्रहरूलाई म हृदयदेखि नै स्वागत गर्दछु र हाम्रो कार्यक्रम सञ्चालन गर्न गइरहेका छु। किन यो अब कहिलेकाहीँ हामी महिनाको पहिलो हप्तामा गर्छौँ, तर यो किन गरिएन भन्दाखेरि अमेरिकाको केसमा जुलाई 4 अथवा अमेरिका स्वतन्त्रता दिवस चाहिँ जुलाई 4मा परेको र त्यो लामो विकेन्ड भएको कारणले गर्दा धेरै मित्रहरू बाहिर घुम्न जाने कारणले यसलाई पहिलो हप्ता नगरेर हामीले दोस्रो हप्ता सारेका हौँ र अरू बेला पनि यो सिरिज अफ प्रोग्राम यसरी भएको हुने भएको भए तापनि अरू अरू हप्तामा पनि गर्न सकिन्छ। हाम्रो सुइटेबल टाइम अनुसार हामीले एनाउन्स गरेर हामी त्यसलाई गर्छौँ भन्ने आग्रह गर्दै म यो कार्यक्रम सञ्चालन गर्नका लागि सुरु गर्दछु र जतिजना मित्रहरू हुनुहुन्छ फेरि पनि यो हात्तीसारियन साइन्टिफिक एन्ड टेक्नोलोजिकल कम्युनिटीमा स्वागत छ। र आज हामीसँग एकदम युवा वैज्ञानिक अथवा यङ साइन्टिस्ट जो चाहिँ डक्टरल क्यान्डिडेट हुनुहुन्छ, उहाँ हुनुहुन्छ अर्जुन घिमिरे र उहाँको सिम्पल केही पोइन्टहरू म अगाडि सार्न चाहन्छु। उहाँ अहिले पनि सेन्ट्रल क्याम्पस अफ टेक्नोलोजी धरानमा एसिस्टेन्ट प्रोफेसर हुनुहुन्छ। करेन्टली हि इज कन्डक्टिङ हिज पिएचडी इन युनिभर्सिटी अफ टेनेसी Knoxville, USA. He has done his master degree and bachelor degree from Central Campus of Technology, Hattisar, Dharan, in food technology. And he has some publication. Some means lot of publication compared to me. He has 11 research papers and 2 books. And he is interested to enhance microwave processing of foods. र अहिले पनि यही सेरोफेरोमा पिएचडी वाले गर्दै गर्नुभएको हुनाले हामी सबैले जति पार्टिसिपेन्टहरू यहाँ भेला भएका छौँ सबैले ताली बजाएर यो कार्यक्रममा चाहिँ तपाईँको आफ्नो पावर पोइन्ट प्रेजेन्ट गर्नुहोस् भनेर स्वागत गरौँ र सबै पार्टिसिपेन्ट सहित हाम्रा आजका स्पिकर अर्जुन घिमिरेलाई हामी सबैले ताली बजाएर यो कार्यक्रम आफूले आफ्नो स्पिच दिनका लागि आग्रह गर्दछु। धन्यवाद।
धन्यवाद भेज सर। मेरो अडियो क्लियर नै होला भन्ने मैले एज्युम गरेँ र स्क्रिन पनि पक्कै सेयर भएको छ। So let me start my presentation. Good evening, afternoon, morning to everyone. I hope you all are doing well. Thank you for joining my seminar. धेरै कुरा त बेस सरले भनिसक्नुभयो। Regarding my introduction, I am Arjun Ghimire. I am currently the PhD scholar in food engineering from the Department of Food Science at the University of Tennessee, Knoxville. I am also the Assistant Professor of Food Technology of Central Campus of Technology, Dharan. So today, I am excited to present my PhD research. In fact, I will give you just the general information on the title, Dynamic Complementary Strategies in Solid-State Microwave Processing. In this presentation, I will begin by explaining the fundamental concept of the microwaves, the microwave oven, and the next generation microwave system, which we call the solid state microwave system. Then I will delve into the dynamic complementary strategies we have developed through our research. And finally, I will discuss the key findings and their implications for the food industry. So let's understand the basic characteristics of the microwave, which is shown in the left side of the figure. As shown in the image, the microwaves fall within the specific range in the electromagnetic spectrum. The wavelength range for the microwave is from 10 to the power minus 3 to 1 meter. In terms of the frequency, the microwaves range from 300 megahertz to 300 gigahertz. This broad range of the microwave involves the various applications, including the communication, radar, and of course, we are going to discuss today, that is the microwave heating. On the right hand side of this figure, we can see the behavior of the electric and the magnetic field in a microwave. As we can see, the electric field and the magnetic field, they oscillate perpendicular to each other and to the direction of the wave propagation. These fields reach their maximum and the minimum values simultaneously, which is the fundamental characteristics of the electromagnetic wave. Let's understand the concept of the microwave, the history, and how it is going on. Taking the closer look at the microwave ovens, these microwave ovens, these days, they are common appliance of the household and the industries. When we look to the history, this had been developed earlier in the 1940s. And the first developed microwave oven, it's called the Radarins. So this technology is not new. In the image on the left hand side, we can see the large microwave which was used in the early stage and it was used for the commercial setting. But with the advancement of the time, the microwaves have become much compact and much efficient. Therefore, they are the indispensable kitchen appliance due to their convenience and speed in heating food. In the middle section, we can see the key components of the microwaves. The key components of the microwaves includes the magnetron, the waveguide, stirrer, cooking cavity, turntable, and door with safety interlocks. The working of the microwave. Let me explain the basic working of the microwaves. So this is the traditional microwave, which we call the magnetron generated microwave oven. The magnetron generate the microwaves in this type of microwaves oven, and these are guided to the cooking cavity by the waveguide. The stereo, which we can see in the figure on the top, just resembling a fan, this helps distribute the microwave evenly. And the turntable, which we use to hold the food, they also rotate by themselves. They rotate in the circular motion. This also aid to the uniform heating of the food. However, these traditional microwaves, which operates by the magnetron, they operate at the fixed frequency. For household applications, typically 2.45 gigahertz, and that limits the flexibility in controlling the microwave energy and the interaction with different types of food. Therefore, I am switching from the traditional microwave to the next level microwave, which we call the solid state microwave. So let's discuss about the potential of this solid state microwave potential. The solid state microwave devices, just like the one which we are seeing in the image in the left hand side, they represent a significant advancement over the traditional microwave technology. These devices are the semiconductors, especially they are the gallium nitride transistors to generate the microwave energy. The main benefits of these solid state microwaves relies on the highly efficient, and they can also operate at higher frequencies, the power levels compared to the magnetron based systems. So in terms of the food processing, the solid state microwave technology can lead to significant improvements in process efficiency and product quality. When we go into the applications, they can be used for rapid heating, drying, pasteurization, and they can reduce the processing times, preserving the nutritional and sensory qualities of the food product. So, these solid state microwave sources, we can do the precise control over their parameters. The parameters which we are working on currently includes the frequency, the power, and the relative phases. The relative phases means is the differential phases. So I have written here for multiple sources. So based on these parameters, the main aim right now in our research is directed to effectively control these microwave parameters. How to effectively handle the frequency, power, relative phases to maximize the overall microwave performance. So this is the periphery we are working on in our research lab. So let's go to the next topic, which we call the smart microwave processing. One of the key features of this smart microwave processing is the use of multi-source solid-state microwave technology. So when we say the smart, we use the accessories like the thermal imaging sensing. In the right hand side in the figure, we can see the thermal camera that is embedded on the top of the oval cavity. On the left hand side, we can see the lab. Okay, it's the solid state microwave generator that we have in the lab. It's the same figure. The solid state generator is connected to the microwave oval cavity. This solid state generator is in fact controlled by the computer controlled programming. In our case, we are using the Python to control the solid state generator. And also the intelligent control comes in the smart microwave processing. In case of the intelligent control, this is what I am going to talk about in my seminar and what my title is focused on. That's basically on the intelligent control of these microwaves I'll be talking on. Okay, let me explain the small sections from the smart microwave processing, how we are conducting in our lab. So the thermal camera, it senses the images of the food that we keep inside the microwave cavity, but it senses the background, the container along with the food. So we use only the food domain, which is the area of interest for us. So we are using the Python programming to create the marks of the food domain and study its characteristics. So that is one example of the smart microwave processing by the thermal sensing camera. This is particularly useful. This type of smart microwave processing is useful in the food industry because this type of the technology can be used to ensure that the ready-to-eat meals are heated uniformly, reducing the risks of the overcooking or the undercooking areas. This type of technology can also be applied in processes like the drying, pasteurization, where precise control over the temperature is crucial. In summary, the integration of food detection and heat pattern recognition into smart microwave processing enhances efficiency, consistency, and overall product quality. Okay, this is the same figure which I'm going to explain on, and I'm going to explain on the two areas where we are working on in the lab. The first area I'm going to discuss is about the frequency-based microwave heating, and in the second phase, I will discuss about the relative phase microwave heating regarding the complementary strategy. So let me start with the first one, that is the frequency-based microwave heating. The figure I am showing here is the overall setup that we have used to study the frequency-based microwave heating. We have the domestic microwave cavity on the left-hand side. So this is the same cavity we use in the household. The solid state generator is connected to the microwave cavity. These are connected by the coaxial cables, and the solid state generator, as stated earlier, these are the semiconductor devices and these have more flexibility and we can operate at higher frequencies. We can control the relative phases through the computer controlled programming. So this is the overall setup we do in our lab. When we talk about the complementary strategy, let me explain you from this frequency dependent thermal contributions. For example, when we heat the food, the image over here is the surface image of the model food. The model food we have used is the potato mash sample. We have heated the potato mash sample at different frequencies. The frequency are varying from 2.40 gigahertz to 2.47 gigahertz in this image. In this image, we can see with the shifting in frequencies, we can see the thermal images patterns are also changing. For example, in the 2.40 gigahertz, we can see the cold spots represented by the blue. It is on the right hand side, whereas in 2.44 gigahertz, we can see the same area is hot, which is marked by the yellow color. So since we saw the difference in the patterns, we came to the concept of this complementary strategy. For example, if we see these two pairs, 2.43 gigahertz and 2.47 gigahertz, in 2.43 gigahertz, on the top right corner, you can see the hot spots, which is circled by the red. Whereas in the last figure, 2.47 gigahertz, we can see the same location has the cold spot on the top. Likewise, if we see on the bottom of the 2.43 gigahertz, the bottom left side, it's hot. But on the 2.47 gigahertz, the same location is cold. So we came to the concept, if we can integrate these two for heating at some point, then definitely the heating uniformity is going to increase. And that is where this complementary strategy concepts arise from. Hence, these complementary frequencies can be selected and delivered microwave power to different locations this way. Okay, let me show you the moving motion of the food that is heated in the three different treatments. The first is the domestic oven, the one which we use in the kitchen. The stationary means the turntable is kept off. The turntable feature is not used. That's why we are using the term stationary. On the middle figure, we can see the smart microwave system, where again the turntable is kept stationary, but this is the complementary approach we are using in this middle figure. While on the right hand side, we can see the same figure like the figure on the left hand side, but this time the turntable is on. So if we see these three treatments, we can see in all of the figures there is much edge heating or the corner heating. But especially when we look at the middle figure, where we have used the complementary frequency, we can use the heat is slowly distributed towards the center. So from this figure, we can say the smart microwave system has more potential than the traditional domestic microwave oven heating, and it can lead to more uniformity and the power absorption. So this is the still figure from the same experiment. We can see there are some of the hot spots in the middle where we use the smart microwave system. So we saw the potential in this complementary frequency strategy. To further test this complementary frequency strategy, we use the various type of the food products to evaluate its validation. The first we used was the single component pulled chicken. In this, we compared between the traditional, which was the magnetron based, and the next level microwave, which is the solid state, at the same parameter condition. We can see we have compared the HUI values on the right hand side. The HUI values means the lower the value of HUI, the better the uniformity. So in this case, we can see the solid state has the lower HUI, which is significantly different from the magnetron system. Likewise, we tested with the two component packages, which is the beef and gravy. In this case, though there was no significant difference, the solid state still had the lower HUI. In the next phase, we saw with the multi-layered lasagna. The lasagna is the Italian meal where they use the pasta, meat, cheese, sauce. So it's a multi-layered meal. In this multi-layered meal of lasagna, we compared between the magnetron and the solid state for the top and the middle layer. Though the top and the middle layer, they do not show much differences among them, but we can see the difference between the heating by the magnetron and the solid state generator. And when we compare quantitatively, we can see the middle layer has a significant improvement in HUI for the solid state. Likewise, when we combine the top and the middle layer, we can see the combination has much significant improvement in lowering the HUI compared to the magnetron based system. Likewise, we also tested with the multiple compartment, which was the second and the last segment. And when we compared the HUI, we saw the significant improvement in HUI in the solid state generator. The same thing went on for the mashed potato. The overall theme of comparison of with these various type of food products, packaging material was to show the developed complementary frequency approach was superior to the traditional heating microwave system. However, there were some limitations in this complementary frequency approach. For example, I showed like to select the complementary frequency, we have to hit the food from like 2.40 gigahertz to 2.47 gigahertz. So we have to create the 7 images at different frequencies. So that is time consuming. The next thing is the frequency dependent thermal contributions. Once they are predicted, they should be updated because if we predict it for the first time, they are likely to change with the heating time and the conditions. The thermal contributions are dependent on the thermal conductivity, the dielectric properties of the food, and in fact the temperature of the heating product. And also in this experiment, we have used only the single pot. So the single pot means it has the relative lower power. So the next area where we have to work on is on the multiple pot. But since we have just started this project has the limitation because we are working on the single pot with low power. The next area, the next promising area, apart from this frequency-based microwave heating, was the relative phase-based microwave heating. So let us understand what is the relative phase heating. The phase difference, as shown in the left-hand side in the animation, the phase difference refers to the relative offset between the peaks and the drops of the two waves. So this interference can either magnify or they can diminish the microwave energy in the specific region of the food within the cooking cavity. Hence, by carefully controlling the relative phase or the phase differences, we can manipulate the interference patterns to achieve more uniform heating. So when we worked on these relative phase experiments, we noticed the temperature change with the relative phase heating, they followed the sinusoidal wave pattern for every pixel point. In this figure, I have shown the three sinusoidal wave patterns, red, blue, and green. So this represents the 3 points in the image. These are the pixel point images. These are the lines from the pixel points. So every pixel point in the heating region, they follow the sinusoidal wave patterns. Keeping this in concept, for example, let's see this figure. So this is the single pixel point. For the single pixel point, if we know the 3 points, like if we hit the relative phase at 0, delta T0, delta T90, and delta T180, shown by the red color in the sinusoidal wave, we can easily determine the other points because there are 3 unknowns in the sinusoidal wave pattern: A, B, and theta 0, theta naught. A is the amplitude, B is the vertical shift in this wave, and theta 0 is the initial relative phase angle. So we have 3 unknowns. So if we use the relative phase heating at the 3 different relative phase angles, we can develop the 3 equations. So if there will be 3 equations with 3 unknowns, we can determine the unknown values A, B, and theta 0. And then we can proceed on to find the values at the other relative phase angles. So we use this novel approach. So this is the novel approach we have used so far. So using this approach, for example, if we use the relative phase heating at 0, shown by the red, at 0 degree, at 90 degree, and 180 degree, we can determine the heating patterns at the other relative phases. The green ones are the predicted ones. The red ones are that are obtained from the experiment. So if we can hit only at the three relative phase, we can determine all the required relative phase hitting. So that is the main advantage of this relative phase hitting. Furthermore, we use this approach to compare with the widely used relative phase heating. And before we introduce the complementary relative phase heating, the fixed relative phase heating and the relative phase sweeping was used by a lot of the researchers. The fixed relative phase heating was just set at 0 degree relative phase by default and conduct the heating for rest of the time. The relative phase sweeping means increasing the relative phase at definite intervals and again carrying the same one. But the one we developed shown in the red, like it was the dynamic one, and it was the smart sensing feature that we use for the complementary relative phase systems, complementary relative phase heating. Whatever the four we put, this senses the complementary thermal patterns, and this keep on changing in the real time. So that is the main advantage of this complementary relative phase heating. So this is the final result after the heating compared between the three phases, the fixed sweeping and the complementary. The complementary is the one we developed. So when we look on these images for the top and the middle layer, we can see the complementary has more dispersed hot region in the centers. So definitely it was the most efficient among the fixed and the sweeping. Furthermore, when we test it quantitatively, we can say the HUI value was comparatively lower in this complementary relative phase heating, which is 0.26, and significantly it was dropped. The power absorption efficiency, which is the power input by power output, it was also found to be higher in the complementary compared to the widely used strategies. And also the range between the maximum temperature and the minimum temperature was lower in this novel approach that we developed. So these were the two fields that we worked on right now regarding this complementary strategy. But in the future, we have some of the ongoing and the future work that we have scheduled. So there are a lot of promising areas that can be worked on, like integrating frequency, power, relative phase, working with the multiple source components. So that is definitely one of the area. The next area arises from the limitation where I had talked about the frequency dependent heating, use of the machine learning algorithms for intelligent control. For example, in frequency heating, we had to collect a lot of the information by hitting at different frequencies. Instead of that, if we can use some of the neural networks in Python, like the CNN module, to predict the hitting at other frequencies from a single or from the double frequency, then that can save the time, and also that can save the computational cost. And also we are working right now only on the domestic system, which is 2.45 gigahertz, and in the later we are planning to scale system, which is 915 megahertz in the future. At last, here are some of the take-home messages from today's presentation. The solid state can generate consistent heating results. The thermal contributions, they are highly dependent on microwave parameters, and I have shown the figures for this one, the images. So these are definitely dependent on the relative phase and frequency. For now, we have tested. The complementary strategy is effective in delivering better heating. The thermal imaging camera, which we are using as the smart microwave heating, they can be integrated into the microwave system for real-time microwave heating performance monitoring. And the dynamic control of microwave parameters, definitely they can be achieved through the intelligent control. So this is how I want to conclude today's presentation. So if you have any queries, information, even in the later, you can contact me in these details. I have my details here. I have my email and phone. You can contact me anytime. With this, I want to wrap up my presentation for today, and that's it. Thank you.
Thank you so much, Arjun Ghimire ji, for presenting very nice information for us. So I want to look at your first slide, then we will go for the question answer. Before that, could you open everybody in the screen, please? So so that we can take a picture of all participants we are in this program today. Could you do, please? Okay, just a second. Yes, we can open everybody in the screen. Oh, I think it's not giving us. So let's go for the question answer. When we stop the PowerPoint presentation, then we will take the picture. Okay. Yeah. Anybody has a question answer? I want to welcome our new participant today, Arpan Shrestha, Puran Thakulla, and Dr. Chudamani Khanal, Sunita Karki. If somebody has a doctor, I don't know here, just Weaver, I know, just I told the doctor. So let's open for question answer so that we will be more clear and we'll get our curious information from Arjun Ghimire. Please.
मैले च्याट बक्समा पनि पाइरहेको छु क्वेसन क्वेरिजहरू म त्यहाँ पनि रेस्पोन्स गरिरहेको छु
सरी म अलि पछि जोइन गरेँ अगाडिको मलाई डिटेल चाहिँ थाहा भएन जस्ट अ क्विक क्वेसन यो फ्रिक्वेन्सी स्विप डिजी स्विपलाई कन्टिन्युस स्विप गरे हो कि डिस्क्रिट गरे हो फ्रिक्वेन्सी
कन्टिन्युस स्विप
त्यो स्टेप साइज कति जति होला केही भन्न मिल्छ
म फिगरै लगाइहाल्छु तपाईँले यो भन्नुभयो होइन हजुर यही होइन
the time the second
time I used was 180 seconds. The phase difference I used was 30 degrees. But yeah, before the completion of 180 degree, 120 second मै यो सबै 0 देखि 330 degree सम्म पुग्छ त्यसले गर्दाखेरि फेरि कन्टिन्यू starts from the previous one, the initial one.
It's a part of IoT, like Internet of Things, kind of.
मैले अलि सुनिन सरको
Like the IoT Internet of Things भनेर एकदम every sensors the gadgets microwave देखि washing machine देखि I don't know सबैलाई चाहिँ AI integrated बनाउन खोजेको छ नि
हामीले अब्जेक्टिभ पनि यो स्मार्ट माइक्रोवेभ सिस्टमको डिजाइन दिएको छ अल्टिमेट अब्जेक्टिभ
स्लाइडहरु शेयर गर्न मिल्छ sorry to ask I just joined only like towards the end so I didn't know what was going on earlier so I just wanna make sure if I'm in the same loop.
I can share this slide, no problem.
Thank you.
Thank you, Dr. Chudamani Khanal. उहाँ वास्तवमा हाम्रो यो कार्यक्रममा चाहिँ नयाँ नै हुनुहुन्छ र आज पहिलो पटक यो कार्यक्रममा जोइन गर्नुभएको हुनाले हामीले स्वागत पनि गरेका हौं उहाँलाई फेरिदेखि सायद अब स्वागत त गर्छौं तर यसरी स्पेशल नगर्न पनि सक्छौं र अरु कुनै क्वेशनहरु यही मौकामा माइक्रोवेभ त हामी घर घरमा एकदम चलाइराखेका मान्छे भएको हुनाले धेरै समस्याहरू हुन्छन्। त्यसमा अब साइन्टिफिक कजहरू हामीले बुझ्न खोज्यौँ भने राम्रो हुन्छ। यही बेलामा हो अब माइक्रोवेभको विशेषज्ञ भनेको हाम्रो एकदम नयाँ जल्दो बल्दो साइन्टिस्ट अर्जुन कार्कीले नै हामीलाई यो क्वेसनको एन्सर दिनुहुन्छ भन्ने मलाई लाग्छ। ल क्वेसनहरू राइज गरौँ।
सर म एउटा क्वेसन सोधौँ?
मजाले
सोध्नुहोस् न।
म चाहिँ खास माइक्रोवेभको त्यति मलाई धेरै आइडिया छैन, युज त गर्छौँ क्या रे होइन। म फिजिक्सकै मान्छे हुन चाहिँ एउटा नन फिजिक्स अथवा फिजिक्स के भनौँ मिक्स टाइपको क्वेसन। यो माइक्रोवेभको एप्लिकेसनले हाम्रो जस्तै भनौँ हाम्रो ट्रेडिसनल कुकिङ अब ग्यासमा अथवा दाउरामा होइन हाम्रो ट्रेडिसनल कुकिङ छ, यो माइक्रोवेभको कुकिङले फुडको क्वालिटीमा त्यस्तो भनौँ न हाम्रो हेल्थलाई इम्प्याक्ट गर्ने गरेर त्यस्तो चेन्ज आउँछ?
त्यस्तो आउँदैन, भेटेको पनि छैन। इनफ्याक्ट के हुन्छ भन्दाखेरि न्युट्रिसनल र सेन्सरी एट्रिब्युट्सहरू जुन हुन्छ फुडको त्यो चाहिँ प्रिजर्भ गर्छ भनेर चाहिँ बरु भेटिएको छ।
थ्याङ्क यू।
हजुर, थ्याङ्क यू सो मच डाक्टर रुद्र काफले। अरू केही क्वेसन नयाँ साथीहरू हुन्छ? मलाई पुरन ठकुल्ला अनि सुनिता कार्की अनि अर्पण श्रेष्ठ पनि हुनुहुन्छ। उहाँहरूले केही क्वेसन गर्नुहुन्छ कि? अरूले पनि, उहाँहरू समेत उहाँहरूले पनि।
रुद्र सरले सोधे जस्तै म पनि अलिकति अफ क्वेसन कि माइक्रोवेभ खास मेन प्रिन्सिपल चाहिँ कि त्यो वाटर मोलिकुल्स अथवा कुनै कोभ्यालेन्ट बोन्डको मोलिकुल्सहरूलाई मात्रै टार्गेट गरेर त्यसलाई हिटिङ गर्ने हो। यो के एक्ज्याक्टली चाहिँ कसरी हिटिङ गर्छ? सरी फर द एकदम लेम्यान क्वेसन है, इफ एनी।
मैले सायद यहाँनिर छ यो इलेक्ट्रोम्याग्नेटिक है। अब यसमा के हुन्छ भने माइक्रोवेभमा चाहिँ दुईवटा हुन्छ, इलेक्ट्रिक र म्याग्नेटिक फिल्ड भइहाल्यो। त्यसले गर्दाखेरि स्पेसली पोलर मोलिकुल्सहरू छ भने, स्पेसली वाटर छ भने त्यसलाई चाहिँ सिफ्ट गरिदिन्छ क्या, विच इज कल्ड डाइइलेक्ट्रिक हिटिङ। त्यो दुईवटा पोल हुन्छ त्यो त्यसलाई सिफ्ट गरिदिन्छ। एन्ड द्याट सिफ्ट इज लाइक 2.45 मिलियन टाइम अ सेकेन्ड। त्यसको ओरिएन्टेसन त्यसले सिफ्ट गरिदिन्छ है। त्यति गरिसके पछाडि त्यहाँनिर फ्रिक्सन कज हुन्छ एन्ड द्याट फ्रिक्सन इज द मेन कज अफ हिटिङ।
हजुर, थ्याङ्क यू सो मच। अरू केही क्वेसन छन् कि डाक्टर खनाल?